Hello, dear students. I welcome all of you in our online lecture 5 on the chapter 3 of paper first, that is D block element for our SYBSc CH301 Physical and Inorganic Chemistry. I again welcome all of you on behalf of our college, Arts, Commerce and Science College, Bodhwad. Myself, Professor Kanchan Damade from Department of Chemistry of Arts, Commerce and Science College, Bodhwad. I hope you all are safe. Now, in this lecture, we will see that why the 4D and 5D series element has similar atomic size. We have already discussed in our last online lecture that the D block element has 4 series, that is 3D series, 4D series, 5D series and 6D series. So in case of 4D and 5D series, all the 10 element of each series has similar atomic size. See the statement here. Radius increases in going from 3D to the 4D metals. If we see the atomic size of 3D element and 4D element, the element have differ in atomic radius. That is, atomic radius are increases from 3D to 4D. That is, 4D metals have larger atomic radius than 3D. What we have to learn here? 4D has greater atomic size than 3D metals. Okay, so radius are increasing, atomic radius are increasing from 3D to 4D metal. But see the second statement, radius of the 4D metal is similar to the 5D metal. What it is? Radius, atomic radius of 4D metal is similar to the 5D metal. In case of 3D and 4D, radius are increasing from 3D to 4D. But in case of 4D and 5D, radius of metals is similar. That is, atomic radius of 4D metal is similar to 5D metals. What is the reason? The reason is lanthanoid contraction. 5D metals have similar atomic size of 4D metals. Means 5D metals have similar atomic size as 4D metals. Why this is so? 5D metal should have larger atomic size than 4D, but this is not so. 5D is equal to 4D metals. 5D metals have similar atomic radius as 4D metals. Why this is so? Because there is lanthanoid contraction. See in this picture, this is 4D metals and these are 5D metals. Here one minute. Here zirconium, see, zirconium has 145 pm atomic size and hafnium has 144. So zirconium and hafnium has similar atomic size. Zirconium and hafnium has nearly similar atomic size. Same way, see this niobium Nb and this tantalum Ta both have similar atomic size. They have similar atomic size. Then again if we see third pair, that is molybdenum and tungsten. Mo means molybdenum and W means tungsten. So molybdenum and tungsten also have nearly atomic size, that is 129 and 130. Same way we see technetium. Tc means technetium and Re means rhenium. So technetium and rhenium also have nearly similar atomic size, that is 126 and 128. So the element of this 4D series and this 5D series have similar atomic size. Similar atomic size. See this, they have close atomic radii. All these 4 pairs means all these 8 elements have close atomic radii, and this close atomic radii is due to this lanthanoid contraction. This lanthanoid contraction. So now here what is lanthanoid contraction? First we have to see what is lanthanoid contraction. This. So what is lanthanoid contraction? It is a gradual decrease in size. See this statement. The gradual decrease in the size with an increased atomic number is called as lanthanoid contraction. See here, this element is from 3D. Consider first atom is from 3D, then second is from 4D, and third one is from 5D. So this is expected here, that we know 3D element have lesser atomic size. 3D has lesser atomic size than 4D. So it is expected that 4D atom should have lesser atomic size than 5D. You have got it or not? See, first atom has smaller atomic size than second atom. Same way, second atom also should have smaller atomic size than third atom. But it is not so. It is not so. See here, 3D has lesser atomic size than 4D. But 4D is equal to 5D. Why this is so? So 4D has similar atomic size like 5D. So here it means 5D. This 5D element are showing gradual decrease in atomic size. This 5D element are showing gradual decrease in atomic size. It is expected that 5D element should have to larger atomic size, but it is similar to 4D. So this confirms that 5D are showing gradual decrease in size, and this gradual decrease in size is nothing but it is lanthanoid contraction. This is called lanthanoid contraction. So again if we repeat this, that first statement said that 3D has larger atomic radius than 4D, but 5D element has similar atomic size with 4D. Why this is so? This is due to lengthenoid contraction. And what is lengthenoid contraction? It is a gradual decrease in the size with an increasing atomic number is called as lengthenoid. So atomic number are increasing from top to bottom. This element has less atomic number than this one, and the second element has less atomic number than last one. So atomic number are increasing from top to bottom. So it is expected that the atomic size should also have to increase from top to bottom, but it is not so. Here first element is greater than second element. First element is less than second, but second element is equal to third element, and this is due to lengthenoid contraction. So now we will see next slide why this is lengthenoid contraction occurred in 5D series. So this is due to poor shielding effect of 4F shell. What is the reason behind why 5D elements are showing lesser atomic radius as compared to 4D? Because of poor shielding effect of 4F shell. Now see, these are 4D series. This one is 4D series and this one is 5D series. So in this 5D series there is a entry of 4F shell. See from top to bottom, from hafnium there is a entry of which shell? 4F shell. But there is no F shell in this 4D series. No F shell. But in 5D series there is entry of what? 4F shell. So this 4F shell has poor shielding effect, and due to this poor shielding effect, these 5D series, this 5D series element shows lengthenoid contraction, and due to this lengthenoid contraction 5D element have similar atomic size as 4D element. 5D element have similar atomic size as 4D element. Now what is shielding effect? We will see what is shielding effect. See, shielding effect is nothing but it is a defense of outer electron. Defense, you know what is defense? Defense means rakshan. In Marathi we say defense, that is rakshan. So the defense of outer electron from attraction of positively charged nucleus. This is nucleus, not nuclear. So the defense of outer electrons from attraction of positively charged nucleus is called as shielding effect. So now see in this picture shielding effect. See, this is the outermost electron. and this one is nucleus. Nucleus has positive charge and these outer electrons all have negative charge. So consider this outer shell is S shell. According to the electronic configuration of d block element, outermost shell is S and innermost shell is D and then F. Consider the electronic configuration of 5D series. Electronic configuration of 5D series, which is written as 4F, then 5D, then 6S. This is the general electronic configuration of 5D series. All the electrons are arranged according to this energy level, that is 4F, then 5D, then 6S. So consider this outermost shell as 6S. This one is 6S. This innermost shell has 4D and innermost shell is 5D and then 4F. So F has poor shielding effect. F shell has poor shielding effect. So the order of shielding effect of all these energy level is like this. S has greater shielding effect than P, then P has greater shielding effect than D, and D has greater shielding effect than F. This means that F has the least shielding effect than S, P and D. So it is said that F has a poor shielding effect. So shielding effect, we know it is a defense. It is a power of defense of outer electron from attraction of positively charged nucleus. So see here, consider this outer electron and this one is a nucleus, positively charged nucleus. These outer electron are getting attracted with nucleus in all the atom. Generally, these negatively charged electron are attracted by nuclear charge because nucleus has positive charge. Now, the inner shells, that is D and F. So the F is near to nucleus here. See, F is near to nucleus here and F has a poor shielding effect. F has poor shielding effect. It means it cannot defend this outer electron from this nucleus, and that's why the outer electron are getting strongly attracted with the nucleus. In which element? In 5D series element. In 5D series element, there is an entry of F shell, and this F shell has poor shielding effect. So this poor shielding effect of this F shell has not so much power of defending this outer electron from the attraction of this nuclear charge, and that's why this nucleus attracting this outer electron very strongly. So due to this strong attraction of outer electron and this nucleus, the size of a whole atom are getting shrink, and due to this shrinkage, the size of 5D series element are become similar to 4D element, because in this 5D element there is a presence of F shell, and F has a poor shielding effect. So due to this poor shielding effect of F shell, the outermost electron are getting attracted are the outermost electron are getting attracted with this nucleus very strongly, and that's why the atomic size are decreases, and hence 5D series element has similar atomic radii as 4D element. So this is the shielding effect. So see, this is a picture which are showing again how the outer electron are get attracted with nucleus. See, these are outer electrons, and this inner shell is F shell and outer shell is S shell. So outer electron are present in S shell here, and the inner shell is F. F has lower shielding effect. That's why this S electrons, all these S electrons are attracted with nucleus very strongly. This is nucleus. It has positive charge. So that's why nucleus are attracting outer electron very strongly. The attraction of outer electron with nucleus are very strong due to low shielding effect of this F shell. This shell is F shell, and F shell has a poor shielding effect. That's why the outer electron are not getting defense from this nuclear charge, and that's why there is a strong attraction between outer electron and nucleus, and that's why 5D element has similar atomic size like 4D, or we can say 5D element has smaller atomic size than expected. Okay, so this is overall shielding effect, how the shielding effect decrease the size of 5D series element, and this shielding effect result into lengthenoid contraction, and due to this lengthenoid contraction there is a decrease in atomic size of 5D element than expected. So this is the reason. Therefore we will say here 5D series and 4D series element has similar atomic size. This is not so in 3D and 4D. 3D has a smaller atomic size as compared to 4D, but 4D and 5D series element has similar atomic size. This is due to what? Lengthenoid contraction. Now you came to know what is lengthenoid contraction. Lengthenoid contraction is a decrease in atomic size, and this lengthenoid contraction is occur due to shielding effect, poor shielding effect of F shell. Now due to this lengthenoid contraction, the size of 4D and 5D series element are similar, and due to this the element of 4D and 5D series have similar number of valency and similar chemical and physical properties. What is that? Lengthenoid contraction. Due to this lengthenoid contraction, the element of 4D and 5D series element have similar number of valency. Similar number of valency. What is valency? Valency is a number of outer electrons. So due to this lengthenoid contraction, 4D and 5D series element have similar number of valency and similar chemical and physical property. So having similar chemical and physical properties, the element of 4D and 5D series element are called as chemical twins. Chemical twins. Twins means looking similar to each other. So now see here, see this first transition series, second transition series and third transition series. First transition series is 3D, second transition series is 4D and third transition series is 5D. So 3D series element, see first column, titanium has 132 pm atomic size. Now see 4D element, that is zirconium, has atomic size 145 pm, which is larger than 3D element. Larger than 3D element. Now same column, see 5D series element, that is hafnium, having atomic size 144 pm. So this is a decrease in the atomic size of hafnium as compared to zirconium. But this is not so in case of titanium and zirconium, that is 3D and 4D. 3D has smaller atomic size than 4D, but 5D has nearly similar atomic size as compared to 4D. Same trend is seen in next column also. See in vanadium having atomic size 122 pm. Second element, that is niobium, has atomic size 134 pm. So vanadium has lesser atomic size than niobium. Now see the element from 5D series, that is tantalum, having 134 pm atomic size. So as if we see the element from 4D and 5D, it is clear that niobium is similar to tantalum, but it is expected that it should be larger than 4D element, but this is not so. So here it is conclude that, and you now know that 4D and 5D series element has similar atomic size. So due to this similar atomic size of 4D element, that is this 4D and 5D element, they have similar physical and chemical properties, and due to this similar physical and chemical properties, they are called as chemical twins. For example, zirconium and hafnium are chemical twin of each other. Same way niobium and tantalum are chemical twin of each other. Molybdenum and tungsten has chemical twin of each other. Same way technetium and rhenium are chemical twin of each other. So the element of 4D and 5D series are chemical twins of each other. Okay. So due to lengthenoid contraction, the properties became same, and properties are became same. That's why all the element from 4D and 5 series are called as chemical twins. Now next we will see ionic radii. Ionic radii. See what is ionic radii. Ionic radii is nothing but it is a radius of any ion. Now if scandium, consider scandium is a neutral atom. When it loses one electron, it will give scandium plus 1 by losing one electron. So scandium is now became ion, and the radius of this ion is called as ionic radii. Now ionic radii follow same trend as atomic radii. You know, atomic radii are decreasing from left to right in periodic table, and atomic radii are decreasing from left to right in periodic table and increasing from top to bottom in periodic table, in group of periodic table. This is group and this is row, or we can say period. This is group and this is period. Now, so what we have to see here, ionic radii follows same trend as atomic radii. So we can say ionic radii are also decreasing from left to right in periodic table, that is from this group to this group. Same way in second series also, ionic radii are decreasing from left to right. And in case of group, ionic radii are increasing from top to bottom. Top to bottom. So this is the trend of ionic radii in periodic table. Remember, ionic radii are decreasing from left to right and increasing top to bottom in a group of periodic table. So this is the trend of ionic radii, which is similar as atomic radii. Now see, the ionic radii decreases with increase in charge of the ion. Ionic radii decreases with increase in charge of the ion. Now see, in this picture all the elements are not d block element, but I have to explain what is the effect of charge on the size of ions. See, this is a neutral atom. Lithium is a neutral atom. When it forms cation, the size of ion are decreases. This is neutral atom. Lithium is a neutral atom. When it loses one electron, it forms Li plus. Now Li plus is a cation. So the size of cation are decreases as compared to this neutral atom. Same way, if we look to this beryllium atom, beryllium has this size 0.90. When this beryllium loses 2 electron, it forms Be2 plus. So Be2 plus. So now there is an increase in the charge as compared to lithium. Lithium has plus 1 charge and beryllium has 2 plus charge in its cation form. So the size of beryllium again decreases because of increase in charge on the ion. Same way, if we see the boron atom, this is the size of boron atom. Now boron can lose 3 electron. So after losing 3 electron, boron has 3 plus charge on its cation. So B3 plus cation has atomic size more decreases as compared to this beryllium and lithium, because lithium has plus 1 charge, beryllium has plus 2 charge and boron has plus 3 charge. So there is a decrease in ionic radii greatly as compared to beryllium and lithium because of increase in positive charge. Now, so this is for cations. Now if we see anions here, these are anions, O2 minus and F minus, S2 minus and Cl minus. These are anions. Now this is the size of atom, oxygen atom. Now if the oxygen atom accept 2 electron, it form O2 minus anion. Now this is anion. These all are cations. These all are cations. So now here is a charge that is 2 minus. 2 minus means there is a decrease in charge. Minus sign indicates that it is decrease in charge. So here charge are decreasing as compared to 3 plus. 3 plus means increase in charge and minus 2 means decrease in charge. So due to this decrease in charge, oxygen anion, this oxygen anion has larger size than its atom. But here lithium atom has larger size than its cation. So oxygen anion has larger size than its atom. It is contrast to each other. Cation has smaller size than its atom and anion has larger size than its atom. Why this is so? Because of decrease in charge, minus 2 charge as compared to the atom of oxygen. Minus 2 means decrease in charge and plus 2 means increase in charge. So increase in charge result into smaller size and decrease in charge result into increase in size. So this is a concept of decrease or increase in ionic radii due to increase or decrease in charges. So anions always have larger size than neutral atoms and cations have smaller size than any atoms, because in cation there is increase in positive charge and in anion there is decrease in negative charge. Negative charge means decrease, positive charge means increase. So in anion there is decrease in charge and in cation there is increase in charge. So decrease in charge result into increase in size and increase in charge result into increase in size. So there is a vice versa relation in between the increase or decrease of charge with respect to ionic radii. So this is the concept of ionic radii, how it is depend on increase or decrease of charges on the anion. Now see next property of d block element, that is melting point and boiling point. Melting point and boiling point are very high of d block element. See, d block element have high melting and boiling point. Why this is so? This is due to closely packed crystal structure. Closely packed crystal structure. This is a closely packed crystal structure. Closely packed crystal structure means the 2-3 layer of atoms in their crystal are close to each other. See this layer, these layers of atoms are very close to each other in their crystals and hence they form closely packed crystal structure. So this closely packed crystal structure require more amount of heat to melt any particular metal. So why the d block element has high melting and boiling point? Because they have closely packed crystal structure. And the second reason is they shows partly filled d subshell. So this is a partly filled d subshell. Some d orbitals are empty and some d orbitals are filled. So this is called as partly filled d orbital. This is called what? Partly filled d orbital. So due to this partly filled d orbital, they can form strong covalent bonding. This partly filled d orbital can form strong covalent bond, and this strong covalent bond result into formation of strong crystals, strong crystals, and hence these crystals of these metals require more amount of heat energy to melt the particular metal, and that's why d block element has high melting and boiling point due to closely packed structure and due to partly filled d orbital. Now next, see the transition element melt above 900 degrees Celsius. All the transition element melt above 900 degrees Celsius. See the tungsten. Tungsten has highest melting point. Tungsten has highest melting point, that is 3410 degrees Celsius. See here in this periodic table, this is the trend of melting point. Trend of melting point. So highest melting point is of this tungsten, W. W has highest melting point. Same way, if we see the zinc, cadmium and mercury, zinc, cadmium and mercury, this zinc, cadmium and mercury has low melting point, has low melting point, that is 120 degrees Celsius, 321 degrees Celsius and minus 39 degrees Celsius. This melting point is for zinc, cadmium and mercury, Zn, Cd and Hg. Hg is for mercury, Cd is for cadmium, Zn is for zinc. So zinc, cadmium and mercury has low melting point. So why zinc, cadmium and mercury has low melting point? Because they have completely filled d orbital. These three elements show D10 configuration. These three elements shows D10 configuration, and D10 configuration is a completely filled configuration. So due to this completely filled d orbital, zinc, cadmium and mercury cannot form covalent bond. Covalent bond is always formed by unpaired electrons, and in case of zinc, cadmium and mercury, all the electrons are paired in d orbital, that is they acquire D10 configuration. In D10 configuration, all the electrons are paired. So this paired electron cannot form covalent bond, and due to absence of this covalent bond, zinc, cadmium and mercury has low melting point, that is 420 degrees Celsius, 321 degrees Celsius and minus 39 degrees Celsius. So remember this. So now the highlight of today's lecture. First, we have learned the point in this lecture is 4D and 5D element has similar atomic size due to lanthanoid contraction. (4D and 5D element have similar size due to lanthanoid contraction. Next, lanthanoid contraction is a gradual decrease in atomic size with increase in atomic nuclear charge. Due to increase in nuclear charge, the atomic size of 5D and 4D series of 5D element is decreases. Then lengthenoid contraction is occur due to poor shielding effect of F subshell. There is an entry of F shell in this 5D series element. So 5D series element shows lengthenoid contraction, and this lengthenoid contraction is occur due to poor shielding effect of F subshell. F subshell. The shielding effect is a defense of outer electron from inner positively charged nucleus. What is shielding effect? It is a defense of outer electron from inner positively charged nucleus. Then ionic size, we have learnt about ionic size. So ionic size of d block element decrease from left to right on periodic table. What is the trend of ionic radii of d block element? That in periodic table the ionic radii of d block elements are decreasing from left to right in periodic table and increasing from top to bottom. Ionic radius also decreases with increase in nuclear charge. That is, cations have small ionic radii than its atom, while ion have larger ionic radii than its atom. Cations are formed by increase in positive charge, that is increase in charge, and anion are formed by decrease in charge. So this increase and decrease in charge result into the increase or decrease in ionic radii. Then at last we have learnt d block element have higher melting point. D block element have higher melting point. This is due to partly filled d orbitals and due to formation of closely packed crystal structure. So all these points we have learnt in this today's online lecture. Hope you have understand very well. If there is any question, you can ask in complaint tab. Okay, so now thank you, take care all of you, stay safe, stay healthy at your home. Thank you so much.